Okay, so in the last lecture video, I introduced the idea of electrophilic aromatic substitution, where we react an electrophile with a benzene ring and we substitute for a hydrogen and replace that hydrogen or substitute that hydrogen with the electrophile. And we talked a little bit about some of the different types of electrophiles that we can generate NO2 plus by reacting nitric and sulfuric acids, SO3H plus using sulfuric and SO3, the fuming sulfuric acid, and we can do halogenation by reacting a halogen like Br2 with something like FeBr3 or AlBr3. So in terms of one of the more important reactions is it would be great to be able to add an alkyl group to the benzene ring. And so if we want to add an alkyl group to the benzene ring, then what we need to say is, okay, great. So what I need to do is I need to be able to add a carbocation to the benzene ring. And if I do that, then sure enough, it'll substitute for that hydrogen. It'll undergo the same mechanism, the same general mechanism as we saw last time. So the question is, how do we generate a carbocation? And this will start with a little bit of review. So how many different ways can I form a carbocation? Well, one of the ways I can form a carbocation would be to take, let's say, a double bond and add to it, let's say H plus, probably from something like H2SO4. But now let's do it in the presence of a benzene ring. And what would happen? We would react the double bond with H plus. We would add the H plus Markovnikov-wise to form a secondary carbocation. And what would happen? That secondary carbocation would react with the benzene ring, and it would substitute for any of the hydrogens. It would substitute a hydrogen with the, in this case, isopropyl group. So that's one way we can generate a carbocation, is by reacting alkene with H plus. Well, I could do the same thing with an alcohol, a secondary or a tertiary alcohol, reacting with what? H plus from, again, probably H2SO4, because I want something that doesn't have a good conjugate base that can act as a nucleophile. So in this case, what would I do? I would protonate the oxygen, form the oxonium ion, and then if it's secondary or tertiary, lose the water as a leaving group to form the secondary carbocation, which would then add to the benzene ring, and it would do electrophilic aromatic substitution. And then we would end up forming, in this case, another molecule of isopropyl benzene. Okay. All right, great. So how else can I form, a carbocation? Well, if you're sitting there thinking, going, well, why don't we just do the same thing with a chloride and then just kind of let the chlorine come off? Well, that's going to be a very slow reaction, and so the easiest and traditional way of actually adding any alkyl halide and converting it into a carbocation is to do what is called a Friedel-Crafts reaction. And it's Friedel-Crafts, and it's not Crafts like the cheese. It's a C instead of a K. That's just one of my pet peeves. So what we can do with Friedel-Crafts is we can take advantage of using either iron or aluminum halides that, in this case, if you remember from the last lecture video, what happened is that the iron tribromide would actually, we'd break the bromine-bromine bond, and give this iron a Br minus, so that we would end up forming a Br plus and the FeBr4 minus. So iron and aluminum will actually pull off the bromine from Br2, and so we could use the same approach here for Friedel-Crafts, for the Friedel-Crafts reaction. So let's say I took isopropyl chloride and I reacted it with, traditionally in a Friedel-Crafts reaction, it would be aluminum trichloride. And so what would happen is we would break the carbon-chlorine bond, and we would end up then forming the carbocation, an AlCl4 minus. And then we would react that isopropyl carbocation with the benzene ring, and it would end up doing a substitution reaction. So again, it would form the isopropyl benzene. And let me kind of complete the reaction, because what would happen is that we would form H plus out of this, right? And so that would react with the AlCl4 minus to basically make AlCl3 and HCl. And so in this case, we would do this reaction and we would do a substitution to put the isopropyl group on the ring. So traditionally, Friedel-Crafts reactions use an alkyl halide with aluminum trichloride to pull the halogen off and make the carbocation. So James Crafts, Charles Friedel. Charles Friedel is also known for Friedel pairs in X-ray crystallography, which is the way that we actually can determine the absolute configuration of a chiral molecule using a solid state crystal of the structure. If you're in the lab class, in my lab class, I talked a little bit about that at the beginning of the spectroscopy portion of lab, the idea of X-ray crystallography, and that it's used to determine absolute R and S configurations, and Friedel was the person who actually did that. So in a Friedel-Crafts reaction, then, we typically do this reaction of reacting alkyl halide plus aluminum trichloride. Unfortunately, this reaction is subject to carbocation rearrangements. And so in terms of looking at what happens there, let's say, for instance, that I took this molecule. Let's say I took an isobutyl chloride and I reacted it with aluminum trichloride and benzene in order to do this Friedel-Crafts alkylation. And alkylation just means I'm adding an alkyl group to a molecule. So I'm going to do this electrophilic aromatic substitution. Actually, we did this reaction when I taught at OU a long time ago. And by mistake, I grabbed a bottle of isopropyl chloride instead of what I really wanted, which was tertiary butyl chloride. Because what we wanted to do was a Friedel-Crafts alkylation of, it wasn't benzene, but it was something similar. We wanted to put a tertiary butyl group on the ring. And so about halfway through the lab, some young scholar, because that's who goes to OU, is young scholars, said, hey, you didn't grab a bottle of tertiary butyl chloride, you grabbed a bottle of isobutyl chloride. And I thought about it for a second. I'm like, it's fine. It'll give the same product. It'll give tertiary butyl benzene. And apparently they weren't satisfied with that answer. So I said, well, I guess we'll make that the post-lab question for this experiment. And didn't make me happy, or didn't make them happy, but they got over it, or they didn't. I don't know. That was my 1 year at OU. Here's what happens. So remember, this is a primary alkyl halide. And so if this chloride is going to be pulled off of the aluminum, I would be looking at forming a primary carbocation. Well, we still have a prohibition against writing primary carbocations, except in mass spectrometry in the lab class. So what will happen in this case is as the chloride gets pulled off by the aluminum, this hydrogen will do a 1,2 hydride shift. And that occurs at the same time. So if I was going to write a transition state for this, here's what I would write. I would write the hydrogen kind of bridging between the two carbons, the carbon-chlorine bond breaking, and the aluminum-chlorine bond forming. So this would be my transition state with the aluminum trichloride. Basically, this chloride's moving as a negative, as an anion, and this carbon will eventually get the positive charge of forming the carbocation. So this would be our transition state. So the hydride would shift over as the chlorine was leaving, and I would end up with my tertiary butyl carbocation, which would then add to the benzene ring and do electrophilic aromatic substitution. So I know for a fact that this reaction does undergo a hydride shift. So you could use either one of these if you wanted to make tertiary butyl benzene. So you can have these shifts occur. And where these shifts typically occur is when we have primary systems. So if one wanted to take benzene and you wanted to add something like butyl chloride or 1-chlorobutane with aluminum trichloride, and for all these reactions you could use FeCl3 as well. But if I wanted to do this reaction, what would happen is that as the chloride got pulled off by the aluminum, then what would happen is one of the hydrogens on carbon number 2, and basically if this is an alpha carbon, one of the beta hydrogens would then shift over, so that what I would end up making is I would end up making the secondary carbocation, which would add to the benzene ring. So I would not get, in this case, I would not get the 4 butyl chloride. I would not get N-butyl chloride, or would not get the straight chain butyl chloride. Instead, what I would get is I would get the reaction of the secondary butyl carbocation. So I would end up forming secondary. I'd end up forming sec-butyl benzene as this reaction, as the product of this reaction. So we cannot, the key thing here is we cannot make straight chained alkyl benzenes from Friedel-Crafts alkylation. That's the takeaway message. We cannot do that because it will undergo a carbocation rearrangement. Okay. Well, so what happens then? What would happen then is that we need an alternative way of making straight-chained alkyl benzenes. And so we'll talk about an alternative method here in a minute for that. So just be aware that carbocation rearrangements will occur. I normally tell you when the carbocation rearrangements will occur, but in this case I will not, because I will expect you to know that if you're reacting a straight-chained alkyl halide with aluminum trichloride, that it will undergo a hydride shift. So you have to know that. That's one case where I won't tell you about the rearrangement. So that's how we can form then that's how we can do the reaction with a rearrangement. So we've talked about the carbocation rearrangements. I want to answer an obvious question, which would be, could I take ethyl bromide or could I take methyl bromide and add benzene and aluminum trichloride and end up making ethyl benzene or making methyl benzene, which is actually called toluene. The common name of methyl benzene is toluene. So can I do this reaction despite the fact that there's no possibility of rearrangement? And this is a primary system, and this is even worse in terms of being a methyl system. And the answer is yes. Yes, I can do this reaction, but then your next question would be, how can you do that without forming a carbocation? Which is a good question. So here's what happens in those cases. What happens in those cases is that when the ethyl chloride reacts with the aluminum trichloride, the carbon-chlorine bond begins to stretch as the aluminum basically gets the chloride. So in terms of sort of a transition state here, I start to form and break my carbon-chlorine bond, and I start to form my carbon-aluminum bond. And as that happens, the chlorine is becoming slightly negative and the carbon is becoming slightly positive. Well, at that point, at some point, you get to enough delta positive charge on this carbon that it will then add into the benzene ring. So you'll get to a point where there's enough delta positive charge so that the benzene ring double bond will then be able to add to that C+, which never really exists. It just exists as a very polarized C delta plus. So at some point as the chlorine bond stretches, you'll get to enough delta positive charge to then allow the double bond to add. And the same thing would be true for the methyl group. The methyl group's carbon-chlorine bond will stretch as the chlorine forms the bond to the aluminum, and at some point you form enough delta positive charge that the benzene ring would then be able to add that methyl group. So that's how a primary or methyl system works. But that's only because these two cannot undergo rearrangement. So there's no way that these can undergo a carbocation rearrangement. On the other hand, if I'm taking my primary system as the chlorine gets stretched out, as the carbon-chlorine bond gets stretched out, then what happens is then the hydride can shift because it's there to be able to shift. So that's one of the limitations in terms of Friedel-Crafts alkylation. So if you want to do a Friedel-Crafts alkylation, just remember that the primary alkyl halides always undergo carbocation rearrangements. And they'll always form a secondary carbocation. Okay, so you just have to be aware of that. Now, Friedel and Crafts also came up with a way to do what's called an acylation. An acylation is basically when you add a carbonyl group with an alkyl group on the other side. This is what's called an acyl. This is actually going to be called an acylinium ion. And if you have seen mass spectrometry fragmentation, we've already been introduced or will be introduced to the acylinium ion. So what happens here again is that the carbon-chlorine bond, this is a carboxylic acid chloride. And just as an aside, a carboxylic acid chloride is made by taking a carboxylic acid and substituting the OH group with a Cl. How do you make that? Well, it's down here. We take SOCl2, or we could use PCl3, either one. Remember, their jobs, like we saw in the last lecture video and the lecture videos before that, is to replace an OH with a Cl. Now, you cannot, if you try HCl here, HCl will not work. So you have to use SOCl2 or PCl3. So that means that if you used SOCl2 or PCl3, you could go ahead and convert any carboxylic acid into the acid chloride and then react it with aluminum trichloride, and it will pull the chlorine, break the carbon-chlorine bond, and make the carbocation, which in this case is an aselenium ion, it's called. Now that doesn't look particularly stable, but it does have a resonance structure. If I take one of the lone pairs on the oxygen and move it down here, I can form a carbon-carbon triple bond with an oxygen in the positive, with the oxygen with the positive charge. So in this case, these resonance structures make the aselenium ion stable, and this carbon plus is what will then add to the benzene ring. So these two reactions actually go together in terms of alkylation and acylation. And if we combine the two of them with what's called a reduction reaction, we can make our straight-chained alkyl benzenes by first of all taking a benzene ring, reacting it with an acid chloride and aluminum trichloride, doing Friedel-Crafts acylation, and we can basically put that aselenium ion on the benzene ring, and we make what is called a phenyl ketone. Phenyl is the name of benzene when it's a substituent. So we can make a phenyl ketone, and now all we have to do is be able to reduce this carbonyl group all the way down to 2 hydrogens. Now notice that this is not, and I'm going to write this is not reducing the carbonyl with something like lithium aluminum hydride, which would actually then make an OH group. This is a reduction of the ketone all the way down to an alkane. And so there's 2 reagents that specifically do this, that take ketones and reduce them down to alkanes. And one of them is called the Clemmensen reduction. So the Clemmensen reduction takes a zinc-mercury amalgam. And so mercury we've talked about a little bit in terms of its toxicity last semester. It's a neurotoxin, but when you add a metal to it, you make an amalgam. So an amalgam basically then is a metal mixed with mercury, and it makes mercury less toxic. There was a time when they used to fill your teeth with a mercury amalgam. Now it's all ceramic, but there was a time, and I probably had those mercury fillings in my teeth at some point. So you take the zinc mercury amalgam with HCl and heat, and by a mechanism that we're not going to talk about, this carbonyl is reduced down to a CH2 group. So if I use Clemmensen here, then I can reduce the ketone down to the CH2 group. Now, just writing Clemmensen isn't enough. You need to know these reagents. You need to know it's zinc, mercury, HCl, and heat. You need to know that reagent will take the ketone down to a CH2 group. But that's all it does. That's its role. Okay, so that's one way to reduce the phenyl ketone. The second way to reduce the phenyl ketone is to do what's called a Wolff-Kishner reduction. And we'll talk about the reacting ketones with amines towards the end of the semester, but if I react the ketone with an amine, I end up forming what's called a hydrazone. And when I make this hydrazone, if I treat it with KOH and heat, then I end up forming this straight-chained alkyl benzene. So in this case, this is called hydrazine. Hydrazine was used as a rocket fuel, probably still is. So you react, and this can be abbreviated as N2H4, KOH, and heat is Wolff-Kishner reduction, and it will again reduce the ketone all the way down to the CH2 group. So either Clemmensen or Wolff-Kishner can be used to make straight-chained alkyl benzene. So let's look at a quick example. Let's say that I wanted to make that 1, 2, 3, 4. I wanted to make the butyl benzene that I tried to make earlier, right? I tried to make butyl benzene before, but with Friedel-Crafts alkylation, I got a rearranged product. So now if I want to make this, what I'm going to end up doing is I'm going to end up coming over here and saying, okay, let's react this benzene with, I'm going to need 3 carbons here, and the acid chloride, I'm going to react that with I'm going to erase that for a minute so I can space them out a little bit better. So I'm going to react that benzene with this acid chloride of a 4-carbon acid along with AlCl3. And what am I going to make? I'm going to do Friedel-Crafts acylation. So I'm going to have the carbonyl, and then I'm going to have the 3 carbons, the CH2, CH2, CH3. And then if I react that with either zinc, mercury, HCl, and heat, remember the triangle is heat, or I could use N2H4 KOH and heat, then I reduce the carbonyl down to the butyl group. So the idea of talking about Wolff-Kishner and Clemmensen reduction is because it goes together perfect with the Friedel-Crafts acylation as a way to make straight-chained alkyl benzenes by using the scheme here of using Friedel-Crafts acylation followed by either Clemmensen or now Wolff-Kishner reduction. Okay. So notice that we're building up our reactions here. We're building up all the different electrophiles that we can add to the benzene ring. And we'll have more as we go along. But what you might want to do is to keep track of those reagents. And actually, I have a summary sheet that I will post that will cover all the reactions that we will do into the next few lecture videos as we get to more and more of these electrophilic aromatic substitutions. But right now we can do a number of different things. So now let's talk about doing reactions on other than benzene. Benzene's boring, right? There's 6 hydrogens. It doesn't matter which one I substitute for. I'm going to make a mono-substituted benzene ring. And if I want to do a reaction now on a substituted benzene ring, so maybe I want to take my molecule, my toluene with a CH3, or maybe I want to do a reaction with a bromo on there, a bromobenzene. What happens when I now want to do electrophilic aromatic substitution or add an electrophile to a substituted benzene? And so the substituent has 2 effects on that reaction. And so we have to understand that in order to be able to understand the rate of the reaction, but also where the electrophile will go. So the first effect that these substituents have is it can cause the reaction to occur either faster or slower. And so we're going to define this as a group that causes the benzene ring to react faster is going to be called an activating group. And a group that causes the reaction to go slower is going to be called a deactivating group. And we'll talk about that as the starting point here in a moment. But it'll also dictate, that group will also dictate where the electrophile adds. So for instance, if I have my toluene with my methyl group here, and I'm going to add, let's add an NO2 plus to this. Okay, if I added an NO2 plus in terms of the regiochemistry, where will the NO2 plus go? Will it go in the ortho position relative to the methyl group? The ortho is the 1,2 position, and there's also an ortho position up here that's 1,2. It could go into the meta position, which is the 1,3 position, and there's also a meta position over here, or it could go into the para position, which the para position would make it 1,4. So where does the group go? And I can tell you right now that if it was just a random thing where it just went in all the possible combinations, I would say that and we'd be done. And we'd save quite a bit of time in terms of talking about reactions, but it doesn't. There's a system to this, and then there's also a reason why that we'll have to talk about. So this group then is said to be the director. And as the director, it tells the NO2 where to go. Do you go ortho, do you go meta, or do you go para to me, the methyl group? I'm directing that NO2 plus group. Okay? So these two things are the effect that a group that's attached to the ring, the substituent, plays. And what we're going to do is we're going to deal with the idea of activating versus deactivating first. And then we'll talk about the reasons why those groups direct to different positions. So here is a table that you will have to know of the groups, and they are ranked right now from fastest to slowest. And so in each of these cases, this is based on experimental evidence. So we take a benzene ring with a substituent on it, and we react it with an electrophile, and we measure the rate of reaction. And what we find is that when you have a nitrogen group, an amine group on the ring, it goes the fastest. When there's an oxygen group, it goes second fastest. When there's a benzene ring, it goes third fastest. And when it has an alkyl group, it goes fourth fastest. When there's just a hydrogen on the ring, all four of these go faster than benzene. So benzene is kind of our baseline here. And then once you get beyond benzene and you put a halogen on the ring, the reaction goes slower than benzene. Any carbonyl will then go slower than that. A C triple bond N will go even slower. Our NO2 group will go even slower. And then finally an NR3 plus, which is what's called an ammonium. That actually probably doesn't, that's probably a no reaction. But we're going to keep it as the 10th group. Okay. So these are the groups that you have to know, and you have to know whether they go fast, they cause the benzene ring to react faster or slower. Now, in terms of the activating and deactivating terms, that's what we use. So we say all the groups that react faster than benzene are activating groups, and all of the groups that cause the reaction to go slower than benzene are called deactivating groups. Now, what causes a group to be activating or deactivating. In order to understand that, we have to look at the basics here. And we basically have to say, okay, my electrophile, my benzene ring is my nucleophile. So how can I make the nucleophile react faster? Make it more nucleophilic. How do I do that? Make it more electron rich. Okay, how do I do that? Well, I do that by pushing electron density into the ring. I put a group on the ring that will push electron density into the ring and make it more rich. On the other hand, if the reaction goes slower, what does that mean? That means instead of pushing electron density into the ring, I am withdrawing electron density. So in this case, this is what is called an electron withdrawing group, whereas over here it's an electron donating group. Okay. So groups that withdraw electron density are going to make the reaction go slower. Groups that make the reaction go faster are electron donating groups. Okay. So experimentally, that's what we found. With everything basically in organic, you have an observation about a reaction, then you have to figure out a reason why. You have to explain it. And so we're going to go through and we're going to explain how these four groups are electron donating groups. And we're going to talk about how these groups are all electron withdrawing groups and the mechanisms by which they do that. Okay. The nitrogen does cause the reaction to occur the fastest. And I just, as a sort of practical, as a story, when we had a master's program, it ended probably between 20 and 15 years ago. When I first got to John Carroll 26 years ago, we had a master's program, and one of the master's students was one of my TAs in the lab, and she was doing electrophilic reactions she was trying to add an I+ to the ring. And so she said, well, what reaction can I get to go the fastest? And I said, well, in lecture we talk about a nitrogen group being on the ring, that will cause it to go the fastest. So she goes, oh, okay, maybe I'll try that out. So then I didn't see her for a couple days, and then I said, oh, by the way, how did that work out? And she goes, oh, it reacts really fast. Because when I added it, it basically reacted so fast that it just boiled stuff all over the hood and might even shot some stuff onto the top of the hood. And I said, I guess it's really active then, isn't it? So that's where we need an ice bath. And we need to remember that, yes, this does activate the ring. So that is the most reactive. And now we have to, unfortunately, it's not just good enough to say, why? Or it's not good enough to say, oh, that happens. No, we need to talk about why. And so, as I said earlier, if we push electron density into the ring, the reaction's going to go faster. And if we pull electron density out of the ring with an electron withdrawing group, the reaction's going to go slower. So now let's get into the nitty-gritty details, because that's where the fun is. Okay, let's talk about electron donating and withdrawing groups, and let's first of all talk about how can that happen? How can you push or pull electron density? Well, there's two mechanisms. One is called induction and one is called resonance. Let's deal with induction first because that's the simplest one that we've actually already done. So it's time for some review. What makes a double bond or a triple bond more stable? If you said more substituents, you're correct, right? More alkyl groups. More substitution, more stable. Why? Because pushing electron density into the double bond makes it more stable. Pushing electron density. So we've done this. How does that happen? Well, the hydrogens become slightly positive, the carbon becomes slightly negative, and what does it do? It pushes electron density into the carbon through that carbon-carbon sigma bond. And so the double bond becomes more electron rich and the double bond becomes more stable by induction, by the C delta minus pushing electron density into the ring. Okay, can I withdraw electron density? So I should apply this to the ring and say, okay, when you attach an alkyl group to your benzene ring, what happens? Same thing. Hydrogens become slightly positive, and the carbon becomes slightly negative, and then it pushes its electron density into the ring. Okay, so not a big deal. That's induction, but now I'm giving it a name. Can I do the same thing by withdrawing electron density through induction? Yes. What if I attach a halogen to the ring? What happens? Well, that halogen is delta minus. How did it become delta minus? Because it took some of the electron density away from the carbon and the ring. So now it's withdrawing electron density through the sigma bond, through an electronegativity difference, which is called induction or inductive withdrawal. So you can have inductive donation and inductive withdrawal. Okay, so we've actually kind of seen that in the past. And as a matter of fact, I'm also going to unfortunately take a moment here to talk about our Diels-Alder reactions, because when we left those, what we said was that if you wanted to make the reaction go the fastest, what you needed an electron donating group on the diene, and you needed an electron withdrawing group on the alkene. So certainly there's more than methyl and halogens, and yeah, every one of these is an electron donating or withdrawing group, and hydrogen again is the baseline. Okay. So what's the other mechanism? The other mechanism is called resonance. And so by writing resonance structures, I'm either pushing or pulling electron density in or out of the ring by forming different resonance structures. Okay, so let's take these top to bottom. Let's start with nitrogen and go down the line. And where possible, I'm going to kind of combine groups together to show you their mechanism. So let's start with the nitrogen and the oxygen. That basically, those are atoms that have lone pairs on them. So let's start by saying, what happens when I attach an atom with a lone pair? Now you might say, but I'm adding a nitrogen, right? Isn't the nitrogen going to be slightly negative? And wouldn't that pull electron density out of the ring? Yeah, by induction. But it's going to push electron density into the ring through resonance. And what we always find is that resonance effects are always more powerful than induction is. So even though you put an electronegative element like nitrogen on the benzene ring, this resonance donation dominates. And how do I know that? Because the nitrogen and oxygen groups react faster than benzene. So I know it's an activating. I know it's pushing electron density into the ring. So here's how that happens. Basically, I can think about the lone pair and resonance structures that I can draw where I can take this lone pair of electrons and move it here to form a nitrogen or oxygen double bond, but then I've got to break this double carbon-carbon double bond and give that pair of electrons to the carbon to form a minus. Now, notice you're saying, but none of these resonance structures are really strong, or none of these resonance structures are really stable. Yeah, I get that. But this is how we explain how a nitrogen or an oxygen group is activating, is because of these resonance structures that cause some electron density to be pushed into the ring. Okay, so I can form then these three resonance structures by taking this pair of electrons on this carbon, using it to form this double bond, and then taking this bond and breaking it and putting that negative charge on this carbon. Then go here, and then put the negative charge up here. So the net result then is that I have, at the expense of the nitrogen, I have given this benzene ring slightly more electron density and making it react faster. It doesn't take a whole lot. Okay, so that's how a nitrogen group and an oxygen group donate their electron density, and in forming these resonance structures, I have pushed electron density into the ring and made it react faster. Okay. If you have another benzene ring attached, you can do the same sorts of things. You could take this pair of electrons, form a double bond, and move this pair of electrons out to this negative. And so then you could continue to do that, so that what you would end up with is, at the expense of one ring, you make the other ring slightly negative. Again, this is an explanation of how this ring then is more susceptible to electrophilic attack. And for our benzene ring, just to skip ahead here, we've already seen that's by induction. So now let's talk about deactivating and electron withdrawal. Well, if I go to my chart, go back up to my chart here, I'm going to summarize these three groups as being an X multiply bonded to a Y group. And you'll buy that for the carbonyl and the C triple bond N, right? What about an NO2 group? Well, an NO2 group looks like this. And it has a resonance structure where the top nitrogen-oxygen bond can be single, and the bottom one. So these are the two possible resonance structures of a nitro group with a positive charge on the nitro. Okay, so these fit the form of X multiply bonded to Y. And in all of these cases, the X is less electronegative than the Y group. So this is going to be sort of a general formula that I'm going to use to explain how these three are more electron withdrawing. Now, in this case, you would say, okay, I get it. A delta plus and a delta minus, a delta plus and a delta minus, and then this nitrogen with a full-blown positive. All three of these do have some induction. They do have some inductive ability to withdraw electron density. And certainly nitrogen with a full-blown positive charge on the nitro group is the reason why it's number 9, why it reacts the slowest. But resonance, again, is more powerful than induction. So how do these groups, how does this X double bond Y group deactivate the ring by, or pull electron density out of the ring by resonance? And so here's how that works. Basically, I could take the carbon-carbon double bond in the ring and use it to form the carbon, and it'd be either carbon-carbon or carbon-nitrogen double bond, but then I've got to move this pair of electrons and give it to the Y group. And what's important here is the fact that the Y group is delta minus, the X is delta positive, so the Y group already has an electronegativity reason to get a negative charge. So this is not violating the electronegativity of the Y group. So then if I do that and draw that resonance structure, notice I put a carbocation here, then it's just like drawing the resonance structures of allylic carbocations that we did a few lectures back. I'm going to take this pair of electrons, move it here. So now I'm going to form the double bond with the positive charge, take this pair of electrons, move it here, and then form the double bond here with the carbocation there. So the net result is that X double bond Y group, by writing these resonance structures, has now left that ring with a slightly positive charge. Better yet, what it's done is it's pulled electron density out of the ring by resonance. So now I've made this ring less reactive because it's not as electron rich as it once was. Okay, so this is how those groups activate and deactivate. So the halogen, we've seen that the halogen deactivates by induction, and the same thing would be true here of a nitrogen group of this ammonium. And I'm just going to comment on that for a moment. So you'd say, well, that's a full-blown positive charge on that ammonium with 3 R groups attached to it, which makes that nitrogen have a positive charge. I think the biggest problem here is not so much that it's pulling electron density out of the ring, but I'm trying to react a positively charged ammonium with a positively charged electrophile, and the electrostatics on that is not going to work. So typically some textbooks won't even talk about this, and they'll just say no reaction. We'll keep it as number 10 for the moment. Okay, so we've talked about how all of those then either donate or withdraw by resonance or by induction. So here's a chart that kind of summarizes that. The three strongest activating groups activate by resonance. The sort of the minimal activating group is induction. And on the other side, the minimal deactivating group, the one that deactivates, I guess, the less, is also induction. And then all of these groups basically are a combination of induction and resonance, but resonance being the dominant mechanism. Okay, so that's how we can explain how the benzene ring is affected by these substituents. Either the benzene ring will react faster or it'll react slower than if there was just a single hydrogen there. Okay. So that was part 1. That was the first idea, is we have activating and we have deactivating groups. The next part is which product do we get, ortho, meta, or para, or combinations of these, if we do this reaction. How does this Y group then affect the percentages of these products that are formed? And basically we are going to call this group, as I said earlier, the director. So it's going to direct the electrophile to either go ortho, meta, or to the para position relative to itself. But what groups do what? Well, fortunately, there's a system for this. And what we find experimentally is that if you take an activated group and you react an electrophile with it, you get a predominance of ortho and para, meaning that you get little to no meta product. Now, you might be tempted here, and at some point we will invoke this, but for the moment, we're going to just say we get the ortho and the para products. You could say, well, what about the sterics here of this activated group and the electrophile adding next to it versus away from it? The sterics will come into play, but right now, if I asked you to write the products of this reaction, if it's an activated group, you'll get both the ortho and the para products. So we call the activating groups ortho-para directors because they tell the electrophile, you go to the ortho and you go to the para positions and form those two products. This is directing. Okay. And then there's this yin and yang of organic chemistry again, right? There's Zaitsev and a Hoffman product, right? There's, you want the most substituted double bond versus removing the least hindered hydrogen in E2 reactions. There is selectivity in free radical halogenation, and then there's pure statistics, right? So there's one and the other. Well, guess what? When we have a deactivated group and add the electrophile, we get very little ortho and para product. We get mostly meta. And so the deactivating group is called a meta director because it directs meta to the deactivating group. So this is why we have to know our ortho, para, meta. Okay. So the halogens are the oddballs here, because the halogens, while they are deactivating groups, they are ortho-para directors. And so experimentally we find that halogens direct ortho and para, but they are deactivating groups. So halogens are the exception to the rule, and we'll have to explain why. Okay, so here's what we do. And what we do is we think about what would happen if I took my prototypical activated group and add my electrophile to the ortho position. And I write the 3 resonance structures that I would get by adding the electrophile to the ortho position. And I would get these 3 resonance structures. But I get a 4th resonance structure whenever the plus charge, whenever the carbocation is next to a group that has a lone pair, because now that group with the lone pair can donate it, and I can form a 4th resonance structure. Okay? So what would happen if I added the electrophile to the meta position? If I add the electrophile to the meta position, the plus charge will be on 3 carbons in the resonance structures, but the plus charge never is next to the atom with the lone pair, so I only get 3 resonance structures here. Well, this is one of these reactions that goes through the major product. The major product of this reaction is formed from the most stable intermediate. And so if you have 4 resonance structures versus 3 resonance structures, 4 resonance structures is more stable, so that'll favor the ortho addition over the meta position. And guess what? If you add the electrophile to the para position, what happens? You again put the positive charge on 3 carbons. One of those will happen to be next to the atom with the lone pair, so I will again get my 4th resonance structure. So the reason that this activated group with lone pairs will donate electron density, or that donates electron density through resonance, the reason that it is an ortho-para director is because you get 4 resonance structures versus only 3 adding meta. More stable intermediate, that gives you the major product. What about a methyl group or an alkyl group? Well, the reasoning here is going to be a little bit more subtle, because I'm still going to get the 3 resonance structures for each addition, and the plus charge is going to be next to the alkyl group when you add it ortho and when you add it para. But there's no lone pairs now to donate to form a 4th resonance structure, so what's the argument there? The argument there is that when I have the plus charge next to an alkyl group, I now have a tertiary carbocation. So when I add ortho, I get a tertiary and 2 secondary carbocations, whereas if I add the electrophile to the meta position, I just get 3 secondary carbocations, and when I add to the para position, I get 1 tertiary and 2 secondaries. So overall then, I do get the more stable intermediate. I do get the more stable intermediate when I add the electrophile to the ortho and the para positions. Okay, so that's the reasoning for the alkyl groups. All right, now what's the reasoning for a deactivated group? And again, I'm going to use my X double bond Y group where my X is slightly positive and my Y is slightly negative. What's the reasoning here that I get only the meta product? Well, as you saw from the last case, when I add the electrophile to the ortho position, the plus charge ends up next to the substituent. Now in this case though, putting the plus charge next to an X double bond Y group, remember that X group is partially positive. So putting a positive charge next to a partially positive charge is unstable. So unstable that I'm going to treat this resonance structure as if it doesn't form. That's why I'm putting the big slash through it. So in this case, I only get really 2 stable resonance structures. So now when I add the electrophile to the meta position and I get my 3 resonance structures and none of them are next to the X group, that's good, right? Because now I've got all 3 resonance structures being stable. And then, of course, if I add to the para position, the plus charge is going to end up next to the delta positive carbon or nitrogen, and therefore that intermediate or that resonance structure is not going to be stable. And so then I'm back down to getting 2 resonance structures. So in this case, the positive charge being next to the substituent is bad. It causes that resonance structure to be unstable. Whereas when it was sitting next to a group where it could form a 4th resonance structure or a more stable tertiary carbocation, that was good. So that's our reasoning for why the deactivating groups of this form are meta-directors and the activating groups are ortho-para-directors. Now we got to deal with halogens, though, because halogens are the oddballs. So it is a deactivating group by induction, but the halogen has 3 lone pairs. So it's going to look like that generic form of the X with lone pairs. So what that means is when I add the electrophile to the ortho position and put the plus charge next to the bromine, I'm going to get a 4th resonance structure. Now, is it stable? Not particularly, but just enough to make this more stable than just having 3. So the bromine halogens are deactivating by induction, but they fit the form of an ortho para-director. And so therefore halogens are ortho-para-directors despite the fact that they are electron withdrawing. Okay. And same and this for the meta and for the para. Okay. So coming back here then, this is the table that we need to know. And there'll be an online quiz where you'll have to be able to rank these groups, and you'll have to be able to not only rank them from number 1 to number 10, but tell me whether the groups are activating or deactivating, whether they are activating and deactivating by induction or resonance. What's more important is, are they ortho-para-directors or are they meta-directors? Okay. This table is a little bit more extensive, and it has some other groups on here that I haven't necessarily talked about, but makes sense. So for instance, if you had an ester with the oxygen group attached to the benzene ring, you would look at that and go, oh, the oxygen's attached to the benzene ring, therefore it's activated. Whereas if it was the benzene ring attached to the carbonyl part of the ester, it would be deactivating. So with esters, you have to be careful. And same thing's true with amides. When the nitrogen is attached to the benzene ring, it's activated. When the carbonyl group is attached to the benzene ring, it's deactivated. And it was actually one of these compounds that Jill had done, had added the iodine to, that basically splattered all over the lab. She used one of these compounds. Now, the reason I show you this table is because the SO3H group that we learned how to add by using SO3 and H2SO4, that group is a deactivating group because it fits the mode of X double bond Y. So it is, it's a deactivated group. These groups of CF3 and CCl3, those are very strongly deactivated groups, but they're very strongly deactivating through induction. So fluorine, 3 fluorines is going to pull all the electron density. It's going to pull a ton of electron density out of carbon, making it very delta positive, which means that carbon is going to pull electron density inductively out of the ring. Same thing would be true for a CCl3. Okay. So the chart that you really need to know is this one. Okay, so now we can do reactions with monosubstituted rings. So let's talk about that, and then we'll work our way into the disubstituted ring. Let's do a problem here. Let's say I've got a methyl group, and I'm going to add HNO3, H2SO4 to this molecule. The first step in answering this problem is to say, what electrophile is this reagent forming? NO2 plus. Now the question is, does that NO2 plus add ortho and para, or does it add meta? Okay. So am I going to get these two products? Or am I going to form the meta product? And you know what? I think it's time for a quiz. So the video is going to stop and I'm going to poll you. Is it going to be ortho para or is it going to be meta? What do you think? Okay, so remember the group on the ring is the director. So what kind of group is a methyl group? It is an activating group, which means it's an ortho-para director. So it's going to direct the nitro group to the ortho and para positions. So the ortho and para products are going to be our major product. Now, if you said that the nitro group goes meta, I think I understand your reasoning. And if you're a person who's like, oh no, you're going to explain to me how somebody got the wrong answer, I don't need that, then put your fingers in your ears or take your earbuds out. Okay, I warned you ahead of time. Now, when I give this problem first to clear up a misconception that sometimes people will get. Why do they think that the nitro group added meta? Because they've confused the group that's being added with the group that's directing. The group on the ring always does the direction. The group that's being added does not direct itself. Okay? So I'm trying to beat around the bush here. The nitro group, yeah, if nitro was on the ring, it would be a meta director, but nitro is not the directing group, it is the group that's being added. So the group that's on the ring always does the direction, not the group that's being added. Okay, so that's why orthopara is the major product. Okay, so that's how we do the reaction. There's a lot of practice problems. You just need to know, is this group activating or deactivating? And then, okay, I'm going to add the group either ortho and para. For the moment, we'll add both ortho and para, or if it's a deactivated group, it's going to add meta. Okay. So that's how we handle a mono-substituted ring. But what about a di-substituted ring? What about taking a methyl group and something like let's do a C double bond O OH group. And let's say I add that same HNO3 H2SO4. Okay. So where is the, and first step is, this is an NO2 plus, where does that NO2 plus, where's it going to add? And so the book uses a method that I used to teach until a student pointed out the fact that it was unnecessary. So here's what the book says. The book says that basically what you would want to do is to look at each group and figure out where they're directing to. So for instance, this methyl group is an ortho-para director, so it's going to direct ortho to itself, and it's also going to direct para to itself. And then this carboxylic acid group is going to point where? Well, it's going to point meta to itself. Where there's already a group, you can't put your electrophile. So this carboxylic acid group is going to direct here. Now, if the two groups were directing to the same position, then there would be no question, right? That's where the electrophile would go. But if the groups point to opposite directions, then who wins? The group that is highest up on the chart wins. So in other words, the group that is number 1, the higher group on this chart, wins. So really this chart should be from 1 to 10 vertically, but I think we'll use that in the next lecture video. We'll have a chart that looks like that. But basically, the group that's higher in number is the one that's going to win. So in this case, the methyl group wins. Now, you could say, well, if they're both activating, the one that's more activating. If it's an activating versus deactivating, activating wins. If it's two activating groups, the one that deactivates the less wins. How about just the one with the higher number? And so in this case, the methyl group is the director. So I would get add the nitro group ortho, and I would add the nitro group para. Now, why didn't I write the product adding to this ortho position? All right, there's a prohibition. You never add between 1 and 3 di-substituted groups. Okay, you never add in between groups. So that position is not allowed. It's a very simple reason. Sterically, the electrophile just can't get there. So you never add between 1 and 3 disubstituted groups. So that means we would not form the product here. Okay. Now, years ago, and I still remember the student. She's a doctor down at Akron Children's Hospital, and Dr. Muscati, our biochemistry person, was actually, I think, Facebooking her back and forth, trying to see if she was interested in coming in and giving a talk to students. Danielle, she raised her hand one day in lecture when I did this, and she goes, "Is this really necessary?" And I said, "Go on. What do you have another method to propose?" And she's like, "Yes." And this made perfect sense because she was pretty much a cut to the chase person. In lab, in and out. So she said, "Well, if ultimately they point to the same place, and that's where the electrophile goes, and if they're pointing to opposite positions, the group that's the highest activating is going to do the direction. Why don't we just go with the group that is the highest director on the chart and not even worry about anybody else?" I'm like, that makes sense to me. So since then, that's how I've taught it. Well, except to show you what the book does so that I can say there's a better way, and it's Danielle's way. So she proposed, hey, just let's use the group that is the one that is the highest on the chart. And what happens if I have that same group? Well, let's look at a couple more examples here. So that actually is a better way of doing it. And like I said, I've abandoned my way of doing it. So let's say I had this. And I'll just use HNO3, H2SO4. There are plenty of these as practice problems that you can do. So again, first step, what am I adding? I'm adding an NO2 group. Where am I adding it? Okay, of these two groups, which one is the highest on the chart? This group. How do I know that? Because I know the chart after 20-some years. You have to know the chart as well. What kind of group is this? It's an activating ortho-para director. So it's going to direct ortho and para, and over here this ortho position is already taken up by the bromine. So that means that I would end up with my nitro group here, and the nitro group there. And so that's the two products that we get. If they are equal groups pointing in opposite directions, so let's say I had a CH3 group here and I had a CH2 CH3 group here. If these groups are pointing in opposite directions and I was adding an NO2+, then we would get a whole mixture of products. If these are equal, then that means this ethyl group is pointing ortho, para, this methyl group is pointing ortho, para, and so I would get 4 products. I would get all 4 products of that reaction. So when they're equal and pointing in opposite directions, then you get a whole mixture of products. Okay. So that's how we handle when more than one group is on the ring. Right. And I'll just do one more reaction to illustrate how sometimes complicated, but how sometimes not complicated this is. So I'm going to take toluene and I'm going to add an NO2 plus group to it. And so I'm going to form the ortho nitro toluene and the para-nitrotoluene. And now I'm going to treat this with another equivalent of HNO3H2SO4. Both of these products I'm going to treat with that. So I'm going to add another NO2 plus to it. So where is this group going to direct? It's the methyl group. It's going to direct ortho and para. So that means that I'm going to end up now with, I'm going to have my methyl group here with my nitro group there. So I'm going to have the nitro group adding to the, to the para position, not the I'm going to have the NO2 group there. And I'm going to have the NO2 group added over here. Over here, where's the NO2 group going to add? The methyl group is directing ortho, but there's already a group at para. So I'm just going to get a single product out of this. And then I'm going to take all of these guys and I'm going to do a third nitration. And when I do a third nitration, I end up with the same product. I end up with trinitrotoluene. Which is an explosive, right? TNT. I love how with the peroxides, when I write boom, everybody decides to write that reaction. Or sorry, the boom came with the ether plus CO2 and or plus the ether plus O2 and a flame. The boom. Trust me, I've been doing this a lot of years. Everybody decides to put the boom after the CO2 and H2O. That's just natural, and still amusing after all these years. Same thing's true for the TNT. So this is the way that TNT was made as an explosive. Now it's actually not what Alfred Nobel made, because Alfred Nobel made nitroglycerin and put the nitroglycerin into clay and made sticks out of it and made dynamite sticks, because it was the Nobel Dynamite and Explosive Company. And that's the same Alfred Nobel that has the Nobel Prize. Upon his death, his family fortune, besides what was still, the Nobel Company still exists, but he established the Peace Prize and the Prize in Chemistry and Medicine and Physics. And it was partially because of the fact that, it was a family company and making explosives is kind of risky. So a lot of people got blown up. And if you have any kind of Swedish ancestry like I do, Alfred Nobel is probably related to you. So it turns out he's like sixth cousin, so many times removed from my great-grandfather. So I have a few Alfred Nobel things, not from him, but just things I've found through the years. So this is the way people made TNT, and then other people tried to do electrophilic aromatic substitutions to make compounds that looked like TNT by putting nitro groups on the ring. And my final point on this is why is this dangerous to make? Well, number one, it can explode. Yeah, okay. But the first reaction, piece of cake. Activated group, nitro reacts really fast. Now I put a deactivating group on the ring. How am I going to get the second nitro group on? I'm going to have to heat it a little bit. Then when I got two nitro groups on the ring, two deactivating and one activating, I'm going to have to heat it a little bit more to get that third nitro group on the ring. And you can kind of imagine that if we're in a situation where, there's a fine line between heating and booming, that you might cross the line and get one or the other. So as we add deactivated groups to the ring, we basically have to then heat it to get that third nitro group on the ring. Okay. So that's electrophilic aromatic substitution part 1, because we need to learn a few more reactions, but that's how we have activating and deactivating groups and how we can know where to add the different groups for a monosubstituted ring as well as for a di, or even in this case a tri-substituted ring. Because what I didn't say was the methyl group is the director all the way around. So even with two nitro groups, it's directing the third one there, there, and there, which is why we get the same product. Okay, so in the next lecture video, we will talk more about the electrophilic aromatic substitutions.